While most names in civil engineering belong to builders of bridges or towers, Albert Atterburg was a man who found his legacy in the mud. Born in Sweden in 1846, Atterburg wasn't actually a geotechnical engineer. He was a chemist and agricultural scientist. His primary interest was in the classification of soils for farming, specifically figuring out why some clays were easy to plow, while others were a sticky nightmare. In the early 1900s, he realized that the behavior of fine-grained soil wasn't just about its mineral makeup, but was fundamentally dictated by its water content. Before Atterburg, soil classification was largely subjective and messy. He changed the game by defining specific states of consistency: solid, semi-solid, plastic, and liquid. He observed that as you add water to dry clay, it transforms through these stages. The limits we use today represent the critical thresholds of water content, expressed as a percentage of dry weight, where these transitions occur. For an engineer, knowing these limits is the difference between building a stable foundation and watching a house slide down a hill. The liquid limit is the moisture content at which soil stops acting like a plastic solid and starts behaving like a viscous liquid. In modern labs, we use the Casa Grande cup to determine this, but the principle remains Atterburg's. He sought the point where a groove cut into a soil sample would close under a specific amount of kinetic energy. If a soil has a high LL, it usually indicates a high clay content and a high potential for shrink-swell behavior, which can wreak havoc on North American pavement and residential slabs. Moving down the scale, we find the plastic limit. This is the lowest moisture content at which the soil can still be rolled into thin threads without crumbling. To find this in the field, technicians literally roll the soil by hand on a glass plate until it reaches a diameter of exactly 1/8 inch. If it crumbles right at that thickness, you've hit the PL. This transition from plastic to semi-solid is vital for understanding how much a soil can be compacted or manipulated before it loses its structural integrity. To make Atterburg's observations useful for engineering design, we calculate the plasticity index, PI. This is a simple but powerful subtraction that tells us the range of moisture over which the soil remains plastic. A high PI suggests a soil that is very sensitive to water and potentially expansive. The formula is expressed as shown. By plotting these values on a plasticity chart, engineers can categorize soils into groups like fat clay, CH, or lean clay, CL, according to the Unified Soil Classification System, USCS. It is a testament to Atterburg's brilliance that, over a century later, his low-tech methods remain the global standard. Despite the advent of complex computer modeling and advanced sensors, we still rely on rolling little threads of dirt and dropping brass cups. Atterburg's work bridged the gap between pure chemistry and practical construction, ensuring that every road we drive on and every skyscraper we bolt to the earth is built with a deep understanding of the limits of the ground beneath us.